Another episode of the Common Lisp Study Group. I am your host, Ram Vedam with Atlanta Functional Programming. Sorry for the last couple of weeks. We had a bit of a hiatus, but we're back. This week, we're going to be beginning our discussion on efficiency issues in Common Lisp. This is part three, I believe, of the Paradigms of Artificial Intelligence Programming book, which is going to be dealing with both tools and techniques for optimizing Lisp programs, and naturally efficiency falls into this kind of realm. So a couple of things that the the book kind of defines that I think is important for us to actually remember is dealing with the term itself, efficiency. Usually, when we talk about efficiency, we talk about two types of efficiency, which is speed or runtime efficiency of a program, as well as to a lesser extent space efficiency, especially if you're dealing with optimizing for space when running certain types of programs on, say, limited memory hardware, such as embedded systems and so forth of that. But there's also a third efficiency when it comes to Common Lisp, and that is cost efficiency, which is dealing with, if a particular part of a program or a bigger program is running more critically, using the metaphor time is money, you can actually define the monetary costs of what may happen if you continue running this program and say your current hardware versus buying a more expensive computer. And unfortunately, throughout the history of computing, especially since Common Lisp kind of came out, and let's not even say Common Lisp, even Lisp itself came about. Um, it was saddled with this reputation as being an inefficient language, primarily because of the hardware that Lisp was designed on at the time. All right. Um, and given that a lot of machines and stuff at that time had limited memory and so forth, then Lisp itself was an interactive language. And at that point, it started off as an interpreted language. Unfortunately, it gained this reputation of being much slower than most of the compiled languages at the time, naturally. So, things have changed since Common Lisp kind of came out into the scene in the 1980s, and especially later on in the 90s as compilers became more and more advanced, and the Common Lisp standard kind of became standardized as of 1990. I think it was 1995, if I remember correctly. And so a lot of some of these claims about Lisp being inefficient is a bit historical, and the author does say so. But you got to remember the context at which Dr. Norvig wrote this. This was in 1990, prior to the actual standardization of Common Lisp. Well, ANSI Common Lisp. Let's be honest with that. It's ANSI Common Lisp, not necessarily Common Lisp. Common Lisp technically came out in 1984 with Common Lisp, the first edition, and Common Lisp, the second edition, came out in 1990. Both books were published as kind of organic standards that eventually just became standardized in the final document that we all know has, I think, X3J13. And that standard being available both from the ANSI standard as well as, I think it's open source. You can actually find an open source version of the full standard itself. Um, and with these, a lot of the issues related to at least efficiency and runtime efficiency specifically kind of became somewhat mute due to modern, hardware optimizations and so forth. Still, given what Lisp is itself, has a language, I think it's important to recognize that the author is right in talking about these issues, not necessarily specifically with some of the main reasons that he brings up here, because some of those are more historical consequences, but the general approach of actually optimizing a Common Lisp program still remains true today. The techniques that he brings up in this chapter, at least, when we start looking at this from a lens of a modern, the modern Lisper. One main thing to recognize is the interpretive argument can be more or less be thrown out because most major actively contributed and developed Common Lisp distributions, as far as I know, Their standard libraries and user-defined functions, if you run it at the REPL, are compiled. With the exception of maybe one, and I think it still is true today, and that is GNU C Lisp. All right. So if you use GNU C Lisp, I believe it's still interpreted. Um, Whereas if you're using ECL or Closure Common Lisp or CCL or CMUCL, which is running the Python compiler, or SPCL, which is also running the Python compiler, but albeit a much more newer one with some more advances. Um, all of those, when you define a function, you're getting a compiled function. Okay, that code is properly compiled to the best of the ability of the compiler. If you actually provided it more type declarations, you'll get more efficient code. If you don't, when we talk about cost efficiency, you'll get less efficient code. It's kind of the sort of the spiel of this. All right. A couple of myths that I'm going to just bring up, that one of which I've already talked about is the interpretation piece. But another one is actually um, how certain programs used to be written. Okay, and due to the historical interpretation of of Lisp, a lot of these languages or implementations were very slow. And one particular one that Dr. Norvig calls out is rules and the rule-based programming approach, mainly because of the fact that up until 1988, a lot of implementations ended up that written rule-based systems were either written in compiled languages like Pascal, C, or Fortran, or in Lisp. And in the Lisp one, because the compiles of those rules were compiled into actually data structures that were interpreted later, the Lisp performance tended to be much slower than the compiled versions, which is really a design choice because the language itself is guilty by association. The implementation of the language was written as an interpreter rather than as a compiler, and therefore, obviously, the code that ended up implementing the rules-based system inside Lisp would be naturally be interpreted, right? um, as we go on through this book, both this chapter and the next chapter, we will see more the approach of dealing with compilers. Has a, well, more importantly, Lisp has being both the implementation language of compilers and target language for compilers. So you could do a source-to-source translation and compilation of uh, something that may be considered non-Lisp code to something that is Lisp code. Um, Couple other points that I wanted to bring up just before is things called just standard runtime type checking. This is something that's important to recognize. Okay, um, in runtime type checking, as you know, the majority of Common Lisp the standard library are written as generic functions. Okay, um, and this is clear when we write stuff in the interpreter. Okay. When we write, say, plus xy given an x and a y, we don't need to know the types of x and y necessarily. It can be figured out at runtime. Now, the cost of this naturally is the code itself is going to be a little slower because it's going to add additional type checks inside of the generated assembly code to figure out which type of operation you're actually going to run. But if you ended up deciding, to do something, say like this, sorry, let me just do this, disassemble. Just to show you this, for example, if we just do disassemble plus xy, you'll see that this code that gets generated, wait one second. Uh, oh, right. I have to make that into a disassemble. lambda xy plus xy because of the fact that it requires a function pointer to be disassembled. You could see that this code is going to be fairly generic in its creation. Okay, and the particular thing that you need to look at is this pointer, this generic plus here. All right, now why is that a generic plus? Well, this generic plus is actually a function pointer to code that adds type checks to see to extract the arguments that have been passed in. What types? Look at their essentially tags because in Common Lisp, variables that get instantiated with the tag determining what type of those information of the data it's pointing to. And looking at those tags, it then dispatches to the appropriate set of assembly instructions to actually go in and execute the code and eventually evaluate plus xy. This is very different for folks who are looking at this coming from other languages like C++ because of the fact that in template instantiation, naturally, it determines those types at compile time. Because this is a runtime check, this is probably kind of the best bet. You'd have a tag architecture that keeps track of those variables and then, acts accordingly based on what's actually dispatched, which naturally results in a larger binary, by the way, because of the fact that it needs to keep all that information inside of the binary, right? Now, this is different if you end up taking this, and we've talked about this in the past when we were talking about type declarations with, say, if we ended up doing declare fix num xy, and then we go in and add plus xy here. And in this case, you'll see that the code will get optimized accordingly and ultimately gets to assigned to the assign Alex, assign Bignum in RDX. So this ends up, just becoming, even a smaller, more efficient uh, code than what you would have previously. Okay. And we can even do further stuff here because naturally, I haven't even optimized this. We haven't even ran the optimizer. We could also run optimize speed 0 and it'll do even further optimizations of this. This is just unoptimized compiled Common Lisp code. What is it actually doing? You can see that it is taking the code and arguments and calling just an allocation rather than the actual, and then this will ultimately run the addition too as well. So all this stuff isn't really covered in this chapter, but it is something that I wanted to bring up because this is all part of this chapter really. And as we go along with this, some of the instrumentation stuff that Dr. Norvig talks about also more or less goes through some of these things. But you have a lot of these instrumentation pieces at your disposal, which brings me to another thing, which is um, and it goes actually back to what we were talking about earlier. Um, Lisp encourages, essentially because it is designed by this function style, right? This procedural style, functions calling other functions. Sometimes you might end up having a lot of functions that are recursive in nature. All right. In older systems, historically, many of you may not know this because we're in the 21st century, but in the early 70s and 80s, function calls were very expensive. And in fact, in because of what needed to be saved in some cases, um, they were and if you talk about earlier systems that were non-risk, right? Because when risk came around, we kind of changed how we ended up dealing with function calls in the stack itself. But even in CISC systems, which x86 is one of those, um, you have your stack frame, all right, that holds information about the actual frame that it's about to call. All right, this includes arguments, return address, and so forth. It also keeps track of the stack pointer and the base pointer the previous place, which is the last place that it saves that before it calls this function. You can understand that the size of which of the memory that you needed to actually create a function call ended up becoming pretty expensive. And not to mention the branch instructions and how they were dealing with this is pre-branch prediction in some cases. So those were also included in the cost of a particular function call. Um, Ever since branch prediction kind of was introduced and it's now well understood, um, a lot of what were previously very expensive calls, especially when we're talking about recursion, especially early Lisp where recursion was very encouraged, and even in Scheme, a lot of that ended up, thanks to especially with innovations like tail call recursion, became no expensive than your standard equivalent iterative loop, right? Which we'll end up seeing later on in this book. So it was easy to actually go and create a modern Common Lisp compiler to actually inline functions and deal with a lot of this function overhead very efficiently. Um, Still, there are still many existing list systems that may end up requiring two fetches to get to the actual function pointer code, and so that level of indirection, which is great for um, redefining functions in the interactive runtime, it comes at a cost, which uh, is actually slower runtime performance. Okay. Um, Another thing that I want to bring up, which I don't know if we, oh, is oh yeah, another big thing is probably going to be garbage collection. Um, Garbage collection up until early Lisp systems were basically stop the world garbage collection. Okay, and typically I think it was as simple as just a basic mark and sweep in most cases. Um, Now, most modern systems have implemented some variation of incremental garbage collection. There are many different garbage collection algorithms out there. It's a whole field. I don't know if you guys ask me up front which one any particular distribution is using. You're going to have to look at the source code to figure out which particular garbage collection algorithm they're using. I'm sure they're constantly changing the garbage collection algorithm um, based on usage and commercial use cases. But that said, garbage collection still is a source of inefficiency when you're talking about when you're comparing it to systems where people know where the memory is allocated and they allocate it accordingly upfront, and deallocated accordingly too as well. And the main reason is because it isn't the fact that garbage collection is an inefficiency. It's just that with garbage collection, most people write inefficient code. Um, well, habitually they end up writing inefficient code. They don't, go back and instrument their code, finding out their bottlenecks and hotspots and optimizing them. And as a result, you end up getting an overall inefficient system. But that isn't to say that with garbage collection you couldn't get code that's extremely efficient. Um, it's something to keep that in mind. Um, Another thing is um, and this is a big one. Um, Lisp itself has been historically reputed as a system that was a fully complete environment for both program development and execution. And this is typical of any interactive language that was developed between the 50s and the 80s, right? So, what do I mean by a complete programming environment for development and execution? You could basically think the equivalent of an operating system, all right? I will never say Lisp is an operating system. Lisp is an implementation. Different implementations could be full-blown operating systems, others not. Lisp is a programming environment for the design and implementation and execution of images. Okay, that is, when you start up a Lisp process, you're essentially starting up like a meta virtual machine, all right, that has all of these live objects that could be representing subparts of a larger program, objects that are part of an actual program that are interactive with each other. state that is associated with maybe, work in progress for a given program and so forth. But when you save it to disk, it's going to stop those live objects and save them accordingly to disk. Now, what that means then is most Lisp programming environments and most Lisp implementations give you, and this is not an exhaustive list, um, capabilities for introspection, capabilities for debugging, capabilities for dealing with the condition and restart system. All right, logging utilities. And with hosted Lisp implementations, that is systems that are running on an operating system, you have OS facilities to deal with external operating system services and so forth, and even dealing with external operating system resources. And these are each individual extensions you could think about on top of the actual Lisp system itself. All right. Naturally, this is a huge amount of code and a huge set of running utilities, many of which may not be necessary when you're trying to run a particular type of production code in a particular type or a particular type of program in production. All right. And so most Lisp processes um, are inefficient because they end up ultimately shipping themselves with some of this baggage. Now, newer recent compilers, and I think SBCL is in this camp, although I don't know all the options, support the ability to cut some of these and disable some of these options when you're about to create a production level image. And as we deal with some other larger scale artificial programs, we might, visit this ability to actually look at some of the command line options and be able to actually go in and uh, optimize our code to actually be able to create smaller level images that could start up more and more efficiently. All right. Finally, I think this is something that's important to note. Each particular operations, plus is one of them. There are many others. Lisp operators, there are 25 Lisp operators. Um, it's very difficult for these kinds of operators to deal with cost of various operations. This is what I mean by cost of efficiency, because since sometimes you might be dealing with a generic operation, and Lisp is a complicated high-level language that gives you the ability to deal with mostly generic functions. Um, you Because of dealing with these different types that might be invoking a particular function, there are going to be various costs associated with invoking that function if you didn't provide type declarations ahead of time, which means you need to be able to look at the code and then determine what would be the best way to efficiently encode the necessary information in order to get the same performance type assembly as you would if you were trying to do the equivalent thing in, let's C. And the reason for that is C, due to the fact that you've added static types up front, a general idea on how a particular piece of code could get compiled into assembly language. In Common Lisp, because of the potential level of indirection for how to deal with functions, again, garbage collection, generic functions where you don't have to necessarily provide the types in all situations, these kinds of things will end up, creating potentially different assembly instructions depending upon the place where the particular function is getting invoked. Um, we end up actually, and also this is also compiler dependent. I should actually mention that some compilers will do very different things. So since we're going to stick with SBCL in this case, I'm going to be focusing on SBCL optimizations. I know for folks who are out there, you might be thinking I'm favoring SBCL. It is only because I'm familiar with it. If the Clojure guys want to come in and tell me how to do this in the Clojure equivalent, by all means, put your posts in the comments and also hit that subscribe button while you're at it. And then let me know you've made a mistake. This is how you do the equivalent in Clojure scale. I will correct it. but I'm going to focus on SBCL because this is somewhat something that I've been kind of digging into, just because SBCL is a pretty great mature Lisp implementation to actually do stuff in. Um, One thing to note, and I will say that I'm not an expert on this, is there's still a place where you might end up over specifying your types and your type declarations, and that might also change how the assembly gets generated. But as we delve more and more into Common Lisp and some of these things, um, you will know when to add the appropriate type declarations to get the performance guarantees that you want. And I think it's important to recognize that that will come with practice, and that will come with has using the tools that this chapter goes through, and the techniques this chapter and the next chapter go through. All right, makes sense for folks. All right. So what are we going to be talking about today? Well, we're going to be dealing with in the next hour or so a just some basic things just to begin our discussion on this, just because this and chapter 10 are going to be fairly involved, and hopefully we'll get a lot of questions on this. We're going to be mainly focusing today on caching and memoization, and a little bit on compilation, okay? And then we'll deal with the other two next time. But in general, this chapter goes through four techniques for basic um, runtime optimization or speeding up a particular algorithm, all right? And that is four techniques for speeding up algorithms in Common Lisp. Okay. The first one I think most people have dealt with, but so it's going to be a pretty quick discussion, which is memoization or caching of results of computations. Okay, for later use. And we're going to see some pretty cool things too when we go through this. The next thing is compilation of code, and this goes back to what I was saying: the differences between dealing with the runtime costs versus actually providing and declaring certain things and getting those immediately compiled into assembly. Okay, um, which is going to be advantages is obviously going to be dealing with less work at runtime in terms of checking and interpretation, and in some cases also parsing. All right. A third one is actually delaying computation of results until needed. All right. Or partial results. Okay. Until needed, if necessary. Okay. Now, for folks coming in the Haskell world or are familiar with lazy evaluation, delaying computation of partial results that may never be needed is essentially, I think, another way of saying lazy evaluation. Um, but that's what the book kind of brought up and how it explains it. So I'm going to just stick with that definition so folks can actually refer it to that way. And then obviously, um, the last one is indexing data structures for quicker retrieval. And this one is a big one for folks coming in from, say, data-driven programming and usually databases, because as many of you know, uh, when you're using, say, a data structure like a B tree or something like that, indexing that data structure in such a way for a quick lookup is very, very useful. Especially when you're dealing with records, which may be on a file system, which is in or a particular type of order. So you want to be able to do a quick lookup of those uh, particular records by using the B tree or the hash table data structures for just constant time or even log star lookups of particular values or rows of values. All right. So let's touch base with really the first one, which is um, memoization. Okay. Um, Naturally, this one I'm gonna be covering very quickly, just until we hit one particular technique, which is something that I didn't um, I didn't cover, I think, in the past. And well, we'll just I'll explain it as we go along. So for memoization, we're gonna start with our classic example for memoization, which is Fibonacci. Okay. Um, this is going to compute Fibonacci. Everyone knows what Fibonacci is, right? It's computing the nth Fibonacci number, which is for most people, it goes through 1, 1, 2, 3, 5, 8, and so forth. This is our standard Fibonacci sequence. Um, and this is going to just compute the nth Fibonacci sequence number. And most people are aware that if the code is going to be if n is less than or equal to 1, we return 1. Otherwise, we return plus 50 uh, and minus 1. 50. Oh, wait. Sorry. My apologies. I just realized that I was in the wrong one. Okay. 50 and minus 2. And this is going to go ahead and compute our nth Fibonacci number. All right. Now, as many of you know, just by looking at the code, this is a very inefficient way of writing Fibonacci, mainly because of the fact that we are computing the same thing over and over again for certain numbers greater than, I think, essentially 3. Um, so Fibonacci 5, for example, will require you to call 4 and 3, and then 4 is actually going to call 4 or 3 and 2, and you end up doing a lot of redundant code to actually, I mean, redundant computation at runtime when you try to call Fibonacci. All right. Um, so just to show this just very quickly, you can see if we trace um, 50. I think if I could do this, I'd just do that. Oh, wait. 50 is not a valid function. Sorry, I have to actually say 50 this way. Okay. And now I do 505. You can see this actually go ahead and generate a lot of um, redundant computation here, right? So one thing that we could do for this is we could run, essentially we could create a memoized version of this function. So we're going to first create something that memoizes any function, okay? And this is going to create a closure essentially of fn is kind of what this is. And what this is doing is going to return a lambda of this. But before we do that, we need to first create our cache. Okay, it's going to be a closure that's going to hold a table, which is our make hash table. Because remember, we're keeping a hash table of this, a cache for this for quick lookup, right? And what this is going to do is just going to do lambda x, okay, and it's going to check to see if our you know x has already been computed. And the way we're going to do that is instead of doing f get hash table that you would normally do, you would use get hash table, but you're going to actually leverage the multi-valuable line of the get hash table. So get hash table, I mean get hash from a hash table um, returns actually two values. It returns the value itself and whether or not it's been found. Okay, so we're going to go ahead and add that there, and then we're going to grab the hash x and table. Okay, and what we're going to do is um, we're going to write this. If we actually found it, found p, okay, we're just going to return the value. Otherwise, we're going to set f get hash x table with calling the function on the value. Okay, and this will do our typical um, calculations. All right. So here, what we're going to do is we're going to call now first a function. We're going to create a function first here called def. Well, I'm going to use actually set f. No, I'll just do def parameter. Um, def parameter mem mem fibo. Okay, this is our, and this is going to memoize our fibo function. Okay, and what happens is wait, what did I do here? Fibo is unbound. What are you talking about? I just, oh right, my apologies. I have to actually put the hash quote. There we go. So this here is going to be, if we look at mem5o, this is just a closure, okay? And we'll see how this is going to be um, uh, generating, because we're already tracing fibo, and I'm going to show you the difference between this first. Let me do this very quickly. We just recall fibo 5 just to give you this calculation. All right, and you can see how many calls are actually repeated here. All right, just very quickly. And what we could do here is if we call func call mem fibo 5, you could see that the generation actually is a little bit shorter than what it would be before. Okay, and or even if we do, let's do 503, you could see that the speed up is pretty quickly done, right? It just return. You could see the call and the immediate return, the call and the immediate return, and you can see how it immediately was able to calculate that, all right? And even here with 5, you can see that even now when we call it again, since it's already been computed, it's not going to actually do anything. Or if we call the next operation 6, this isn't going to be too much. It's going to actually do just very quick lookups and returns, right? So this is very useful. Okay, but we could even do more. Um, you could see that here we're still technically, when we don't compute, we're still technically calling these recursive calls, right? And what we'd want to be able to do is also cache those in between, because you know in some cases, those lookups could have been, immediate, almost instantaneous, right, for the function calls. So what we'd want to do is we'd want to actually go ahead and really force what we did here, this memo 5.0, to be the new Fibonacci function. What that is basically um, replacing the function pointer with the memoized version. All right. And the way to do that is twofold. One, I'm going to just show you what the kind of what the book mentions here, so we can look at the code. But this is basically going to create it's going to replace the function name. I mean the function pointer, okay? The function pointer in the global table, all right, the global definition table, because with the memorize function, okay? Okay. So how does that look? Okay. So this is pretty simple. All you do is you and let me just go ahead and write the code and then we'll talk about what this is. Okay. Symbol function. Okay. Um, Let me go ahead and actually call this function name because this is not the actual function itself. Wait. All right. So, um, so let's talk about what this code does. Okay. Now, some of you may have seen this from previous talks that I've done here, but just to review, in Common Lisp, you have a table of symbols. Symbols are objects. Common Lisp is a Lisp 2, which means those symbols will contain um, a value object and a function object. All right. So the symbol object is like, think of it like a class. All right. That has two members. One is called value and function, and the function is a function pointer. The value is actually potentially for values. All right. And this is how it's separated values and functions into two different namespaces. All right. In order to access the function pointer, you have to call symbol function. In order to access the value, you have to call symbol value. Okay, you can actually use this in the REPL actually as such. Okay, you could see if we call symbol function on say 50, you could see that it will actually go and grab the 50 code, and you can actually technically do a fun call on symbol function if you wanted to, if I remember correctly. Function 503, and it should do the same. Yeah, it's going to end up calling the actual function pointer, right? This is going to actually be changed when you go call memorize function name, all right? And what it's going to do is it's going to replace it with the um, memoized version of it. So when we do memoize here, 50, we've effectively now just changed this guy to being a closure with the memoization code. Now, what advantage does this have now? Well, now when we call 505 or 503, it's going to immediately compute it if it doesn't compute it, all right? And if we call it again, you can see that it's instantaneous. If we call 505, you can see that we've now reduced the number of calls, all right, of that we saw before, even the old memoization version, with just 3 calls here, as we would have expected, because we've already computed um, 4, which is 3 plus 2. We can actually go and compute that. We can actually go and grab the next calculation to actually go and compute um, the next value in the code. All right. Hopefully, this is a review for most folks who are following along. But you could see very, very quickly that by just simply changing um, there is oh, okay. Um, so I just saw a comment here. Okay, that's good to know. I'm gonna just keep that in mind. Um, and all right, all right. So this is, like I said, this is just this should be a quick review for most folks who are familiar with memoization. There isn't really nothing much here in terms of calculations. Now, obviously, for those of you um, who are looking at this are saying, well, this is great, but really you could also, do well, let's finish this discussion, and then I'll briefly give a comment about the iterative stuff before we start talking about the next topic. So we just saw memoize, okay, um, and but there's one thing that is kind of missing in terms of the interactive development process that I want to kind of bring up. That is, recompilation still does occur when you try to call this function here that we just created, this memoize on the function name. And that's natural because of the fact that what's going to end up happening is it's looking up the function pointer. You're creating a new function pointer essentially and constructing a new closure. That's going to compile another function and then go assigns that new compiled function over to the symbol function slot of the given function name object. So typically, what you'd want to do is rather than doing what we did here with 5.0, if you want to memoize 5.0, you could also, typically do the following, which is once this memoize function is defined, you could actually go in and say memoize and then just define the function like so, because this is going to create the object in time and then does a single compilation, right, of the function code. Okay. Um, One thing to recognize is for folks who are looking at this is typically where your macro feelers should come off and say, okay, we're generating a macro here. Because I'm sure there are other functions that I don't want to memoize, so we'd end up creating probably a macro, and this is the macro that Dr. Norvig created, which is defun memo, which takes in a function, the arguments in the body, body. And please, folks, body is technically rest, but in macros, it doesn't like using rest. It uses body. All right. And we're going to just create a quick documentation right here, create a memoized function here, just so that documentation can actually give us what this function is, this macro is, and then we could just create our memoize. Okay. And we're gonna do defun, oops, sorry, defun function args body. I think it's, yeah, right. Oh, right. I think I have to actually put a dot here. We'll see. Let me just create a new defun memo fib, and which ends up creating the same code that we have before, but it's just renaming it fib. Okay, if uh, and 1 otherwise plus fib. Um, okay, and we could see this, and it creates the appropriate memoized function the way we expect it to. Wait, it looks like I have to do that. Let's see this. Defun fib. I think that's right. Yeah. I wanted to try something though. There was here a dot that the book had. I'm wondering if that does the same thing. Huh. Okay. Um. So you could define it in two ways. I'm gonna go ahead and define it this way. Wait. At. Excuse me. So now we have our code compiled, and let's call trace on fib 5. Okay, you see that it's computed. Let's try to do fib 5 here very quickly, which is very nice. Fib 6, you can see, very nice. And each call, notice it's still in the same level because it's doing a quick lookup, returning, and then we have our nice little things here. Um, One of the nice things with this approach is now we've essentially allowed us to be able to do a time on, say, computing the 100th Fibonacci number. All right, and you can see that it took less than a second to actually go and compute it. I mean, this is 1,000th Fibonacci number here. All right, and it's pretty fast in terms of quick lookups. All right. I want to briefly mention here um, that the approach that we took here, and there's another one that's kind of interesting that the book created, is this is their typical function, but one of the problems with this memoization approach that we've designed is mainly the number of arguments that we could pass in to actually do the kind of caching that we're doing. So right now we're only using a single argument. So if you're using a functional style, this is technically, a functional style, and you can do but you might want to do, currying and caching in other sort of levels. So the book actually gives us a slightly different but more flexible approach, also to actually deal with a couple of things. One, the inflexibility due to the single argument. Two, um, it's only dealing with uh, arguments that are EQL, in terms of the equality operators. But remember, in common Lisp, there are three types of equality operators. There's EQ, EQL, and equal, right? So an EQ is dealing with, the consing operations and whether or not they're equivalent or not. EQL is dealing with whether or not they are uh, what is it? The values and the objects are EQL, and equal is basically dealing with value equality. Um, and so you want to be able to, in some cases, have a flexibility to choose um, if they're equal or EQL. All right. And so and another thing is for efficiency, sometimes you may want to delete entries from the hash table. All right. Like, for example, you might want to have a time where, previously computed values that aren't used anymore or that aren't used anymore could be used to be it could be removed because they're no longer necessary, just because of usage. And then, you can optimize based on those. So I'm gonna quickly write up the three pieces of code here that will add this flexibility. These are the flexible versions, if you will, of um, the memoization functions. And then we could talk about compilation probably next time, depending upon how quickly we review these. And really, this is a new version of memo. It's going to add two more arguments. You have the function, the name um, of the actual value that you're actually trying to grab. Um, there's a oh, these are keyword arguments. Hold on one second. I think these would need to be keywords. So name, key, and test are going to be keyword arguments. And keywords are basically, they could be in any order. um, so this is also going to be creating normalized version. Okay. And we're going to do the same thing that we did before. We're going to do let table be make hash table with the test being test. And test is basically the test keyword is going to hold which type of equality are we doing? Are we doing EQ? Are we doing EQL? Or are we doing equal? All right. The key keyword here in this argument is going to be talking about essentially the indexing scheme. How are we actually indexing into the given table that we're creating? All right. Um, and what we're doing is in this case is we're using name to store the hash table on the property list of um, uh, the actual underlying table in the closure. Okay. So we're gonna see how this is. This is the first example that I think I'm covering in this podcast or in this stream, if you will, depending upon who you're looking at. Um, in terms of leveraging the property list of underlying Lisp objects in memory. This is very much like in Clojure, and that's Clojure with a J. All right. the metadata property that you've encountered. So folks who are familiar with that, this is kind of the equivalent to that that we're about to see, which I think is pretty cool. Okay, and the reason why we're doing this is because we will have this requirement that sometimes we may want to clear the memoized tables that have been previously computed. Okay. And so in those cases, the ability to be able to clear those out would be useful if we are able to look them up by a particular name that we provided. All right. So how do we do this? So we've created our hash table here. Um, and now what we're going to do is we're going to first go here, make sure I'm in the right order. We're going to first set get name indicator is going to be our memo from, and we're going to use table to actually go and grab it. Okay. And just to show you how this is going to look like before we complete this, this function is in the following code, right? In clear memorize, what we're going to do is we're going to just simply do um, so this function here, clear memorize function name. I'll write the rest of the memorize function in a second here. I'm just going to show you how we're going to clear the hash table here very quickly. Clear the hash table for the memo function. And what this is doing is first we're going to do um, let table be um, get sorry get function name from the memo symbol. Okay, because we put this table inside of the symbol object of the property list of the memo function pointer. All right. So it's keeping track the memo is holding all the tables that that's called inside of the code base inside of its property list. That's what this is doing. Okay, and we'll see what this looks like in practice in a minute. So that's what this is doing. We're gonna grab it and basically if we find it, call clear hash on table. That's it. All right, and this is going to clear that table, all entries from it. Okay, so we got that. We have our set of the table in the property. Now, what else are we going to do we need to do? Well, this is going to now create the rest of the function, which is the indexing scheme stuff that we're talking about. We create a lambda with the arguments, okay, and let's make sure that we add the rest here because we want it to be dealing with it. Now, the main thing here to note, and this is the difference between the other, whereas before we are we didn't whereas before we didn't we only had a single argument for evaluation, and that single argument was the key into this table. This key function, all right, if you will, all right, it's going to be a function that we call on the arguments to determine which key or which arguments of the given function that we're going to index and create this index into the hash tables for. All right, and you'll see how this is going to look like. Okay, so we first create a let. Our key k is going to be fun call on key and the arguments. Again, this is for the purposes of determining the key into the hash table. All right, And then the rest of the code will look the same to you. We're going to go and do multiple value bind, val found p on get hash k table. Okay. And like this. If found p val. Otherwise, we're going to have to call setf on get hash with applying the function to the arguments. Okay. Setf get hash k table and apply function to the arguments. And that's it. That is our multi-value memoized function. Undefined variables with, oh, sorry, not multiple value. My apologies. Multiple value bind. There, better. Okay, so now that's our memo function. Now, what does memoize look like? Well, memoize is going to be the same key arguments that we see here, but there's going to be some defaults. Okay. So the memoize version of this is going to be def on memoize. It's going to take the function name and key is going to be key first. And this is just going to grab the first argument from the list if you think about it. All right. And the second one is going to be default test EQL. And then the rest of the code is going to be pretty similar. All right. We grab setf symbol function name, and then we call on it memo symbol function name. Function name is going to be the name of the key of the table, so we can make it easier to clear it out. And our key and our test, and that's it. Okay. So this is, hold on one second. What is it? Wait, did I? Oh, wait. My apologies. That's because these are keyword arguments. Name, function name, key, and test. There we go. So this is going to do the same thing. I'm not going to go and reiterate, what this looks like. And you could try this on other examples of this, but the basic idea is going to be the same. It's going to end up calling this function, creating this table, storing it for later use, so that you could have different function names and different tables in the property list, and then you can retrieve it. So just to kind of show you very quickly how this might look. We call memoize now on, say, fib 50, okay? And we run this and look at this. Sorry, not file this. We need to go and look at there's a way to introspect a particular symbol here. Not stickers, not trace, not compile. H, a describe symbol. Don't think this is going to look up. Let's see what this does. Okay, this is defined as that. That's what that is. Let me see if I can actually go and say inspect symbol. Memo. Let's see if I can get. There's a way to actually do inspection on. See something. Test. MD. No. 1 second. This is in. No. 1 second. One more time. Let me just make sure. MR. Nope, not that. Where is that? That has to be in. You know what? There might not be a sly inspect symbol. It's probably what I have to do. Control C. Yeah, that's probably what I need to do. Control C, Control C, Shift I. That's probably what I need to. 4. No. Inspect symbol is what I need to do. Oh shoot! I just cleared it. That's not a good idea. Because once you redefine, you've cleared the property list. Okay, so let me recall this memorize FIBO. It's created. Now let's do get name FIBO from memo. See what happens. You can see here I can at least grab it. I wanted to show you the nice cool thing that this actually shows up in the property list, but for some reason I can't remember the exact command to actually go and do that. That's in sly. Hold on a second. Oh, there's a function. There's a question here. What happens if we redefine FIBO after using it? Okay, so the question about redefinition. If you redefined FIBO after using it, there are 2 cases. The first case is, let's say that you didn't call setf symbol function, all right, and you didn't create the memoized version, all right. Then you're just recompiling another function. You're just redefining the function. That, I'm assuming, is not the question you're asking for. You're probably asking the other question. Let's say that you had a memoized version of FIBO defined in your function global definitions table. And then you go and decide, after computing a bunch of stuff, to go and redefine it, right? You've effectively cleared the hash table. You effectively made those into garbage, which means it's going to be collected later on, and you are effectively starting from scratch. So yes, there are cases where uh, the memoized version of 5.0 using the old approach is going to end up resulting in a a redefinition. In this case, though, the new one with the flexible arguments, I don't think that is the case because unless you explicitly call clear memoize, it will not get cleared. In the other case, the reason why it's going to get cleared is because you created a new object, so that our object is now out of scope. All right, so that's the difference there. Um, this is kind of cool property stuff, but yes. Uh, and then there's a B hits ROM's reset button. I don't understand that comment, but okay. That's a that's a that's a cool thing. Okay. I didn't think it would take me this long to talk about the memoization, but we did learn something cool about Common Lisp's programming environment that I thought was really nice, which is symbols have property lists. You could add any sort of metadata on top of these property lists, and that metadata is kept in for the lifetime of the program. So that's probably the precursor to meta, which is the metadata stuff that's in using the caret symbol, I believe, has dictionaries in Clojure with the J. So in the last remaining 8 minutes, are there questions, comments, concerns, insults? Um, okay. I don't have time to start talking the next topic because the next topic is actually fairly involved and it's about compilation of our existing code. So tune in next week when we start discussing um, the compilation and more on Lisp efficiency issues. So I will see you guys next week. Thanks. Enjoy your evening. Peace. Bye.